Hi everybody, this is another video that I'd like to ask you to watch before class when we start chapter 15. And in this video we're going to talk about an introduction to acids and bases. So there are a number of different definitions for acids and bases. The first definition, and probably the most basic, is due to the Arrhenius theory. And in the Arrhenius theory, an acid is a substance that produces H plus ions in aqueous solution. So hydrochloric acid would be an example of an Arrhenius acid because when I take HCl and I dissolve it in water, even though it's covalent, because it's an acid, it dissociates into its ions, and so it dissociates into hydrogen ions and chloride ions, and so because it's producing H plus ions, HCl is an Arrhenius acid. An Arrhenius base is a substance that produces hydroxide ions in aqueous solution. So sodium hydroxide would be an example of an Arrhenius base because it's ionic, so when I dissolve it in water, it dissociates, and it's going to dissociate into sodium ions and hydroxide ions. So because it produces hydroxide ions in solution, it is an Arrhenius base. Now, before we talk about the next definition, I want to say a word about what we call hydronium ions. So it turns out that H plus ions don't exist by themselves in water. And in fact, what happens is when I try to produce hydrogen ions or protons in water, they actually combine with water molecules to form this hydronium ion, or H3O+. And so oftentimes we'll use these interchangeably. So sometimes it's easier just to write H+, even though we need to understand that H3O+ is a more accurate picture of what's going on. And the reality may be even more complicated than this, in that the hydrogen ions may associate themselves with more than one water molecule. But for simplicity's sake, we'll stick with the H3O+. All right, our second definition of acids and bases is a little bit broader, and it allows us to classify more things as acids and bases. And so in the Bronsted-Lowry definition, an acid is something that donates protons, or donates H+. And so again, HCl is an example of that, but to see how it reacts as a Bronsted-Lowry acid, we need to include water in the equation. So now we're going to have HCl reacting with water to form Cl- and H3O+. And so what we mean by donating the proton is, right, I'm starting with HCl, it's going to give this proton up to the water. Right? And so when it gives away an H+, we're left with Cl-, and then the water, because it gained that proton, is now going to be H3O+. Now, an Arrhenius base is something that accepts protons. And so NH3 doesn't really fit into exactly as obviously into in our Arrhenius category because it's got no OH minuses to give up. But if I react ammonia with water, if it is an H plus acceptor or a proton acceptor, that means that the water is giving up the H plus and the NH3, and so when it adds an H plus, it becomes NH4 plus, and the water becomes OH minus. Another term that we use when we talk about Bronsted-Lowry acids and bases is compounds can be amphoteric, meaning it can act as an acid or a base. And water is an example of a compound that can do that. Right? Because if I look at my first equation, right, HCl is an acid, so it's donating the proton to the water. Well, that means that water is accepting the proton. So in this case, HCl is my acid, water is accepting the proton, so it's a base. Whereas in the reaction down here, NH3 is a base, it's accepting the proton, but that means that the water is donating it. So in this case, water is acting like an acid. So water can both be a base or an acid, so we would say that it's amphoteric. Now, a really important concept when we talk about Bronsted-Lowry acids and bases is the idea of conjugate acid-base pairs. And so a conjugate acid-base pair are species that just differ only in the presence or absence of a proton. And so our conjugate acid-base pairs in this reaction would be H2S and HS minus, right? Because the only difference between these two compounds is this one has an extra H plus and this one has lost it. And the other conjugate acid-base pair is going to be ammonia and ammonium because they also only differ by a proton. And so in this reaction, the H2S is giving the proton to the NH3. and so it's acting like an acid. That means the NH3 is acting like a base because it's accepting the proton from the H2S. And so we usually refer to the products as being the conjugates. And so if H2S is an acid, then its conjugate base is HS minus. And the reason we call it the conjugate base, if we imagine running this reaction backwards, right? So if these were the reactants and these were my products, then right, this HS minus is accepting a proton from the NH4 plus. So if the reaction runs in the reverse direction, it would be acting like a base. So we call it the conjugate base of H2S. And so that means that the ammonium is the conjugate acid of the NH3. So H2S is the acid. Its conjugate base is HS minus. Ammonia is acting like a base, and so its conjugate acid pair is NH4 plus. All right, so we're going to do a couple examples. Right, so I don't know what is the conjugate base of HNO3 or nitric acid. Right, and so if I'm looking for the conjugate base, then that means that this thing must be acting like an acid. And acids are proton donors. So to find the conjugate base of something, we need to take away an H plus. So if I take an H plus away from this, obviously the H is gone. And because I took away a plus, I'll be left with a negative, and so the conjugate base is the nitrate ion. If they ask me what is the conjugate acid of this thing, well, if they're looking for the conjugate acid, then this thing must be acting like a base. So it's going to be a proton acceptor, so I need to add an H plus to this. So I'll add an H, and then this will become, because I'm adding a plus, it will become one less negative. And my conjugate acid of the carbonate ion is HCO3 minus, or the bicarbonate ion. All right, one more example, kind of like the first one we did. So we want to identify the acid, the base, the conjugate acid, and the conjugate base. So the first thing we want to do is figure out, like, what are my pairs? Right? So I want to find out what are the two things that differ by just a proton. So in this case, I think it's going to be the this guy here and this guy here. And then the water and the hydronium will be the other pairs. Right? So I know these are the red ones and the blue ones are my pairs, and now I got to decide which ones are the acid and the bases. Right? So when I look at this, it looks like this guy is giving this proton to the water to make the water into hydronium. So if this is giving up its proton, then it's acting like the acid. And if this is accepting the proton, well, I'm sorry, I went out a little bit out of order there. Right? If this is the acid, then its pair must be the conjugate base. Right? And so then this guy, right, he's accepting the proton, so he's going to be the base, and then his partner is going to be the conjugate acid. Okay, so just a couple more things that I want to do in this video. And so what we want to do now is we want to write the equation for the acid ionization of just a generic acid. And we're going to use this a lot. When we just want to talk about a generic acid, we'll use HA because there is no element A. Right? So H is the proton that we're going to be donating, and A is its conjugate base. Right? So this is just the same equation that we've been writing quite a bit here. Right? I've got HA reacting with water. If it's an acid, it's going to donate the H plus, so we'll be left with the A minus behind and the hydronium ion. So next what I want to do is I want to write an equilibrium constant expression for this reaction. And so this is just like what we're doing in chapter 14. It's going to be the concentrations of the products divided by the concentrations of the reactants. Of course, because water is a liquid, we'll leave him out. He'll have a value of 1. And so this would be the equilibrium constant expression for this reaction. And so the only difference between different acids will be, what is the conjugate base and what is the exact acid. And I call this a Ka. So this is just an equilibrium constant because it is for a specific type of reaction, it's for the acid ionization, we call it a Ka. Right? And the size of the Ka tells me about the strength of the acid. Right? And so a stronger acid is going to be one that produces more hydronium ions in solution. Right? So that makes sense, right? If the numerator is bigger, if this H3O plus is bigger, then the Ka is going to be bigger, and so it's going to dissociate more. And so we often break up acids into two categories. We have strong acids. These are acids that completely dissociate into solution. Right? All of the reactants are converted into products. So all of my HA gets converted into hydronium and A minus. Right? And so if this sort of represents that pictorially, right? So this is before the dissociation is allowed to happen. Obviously, I only have the acid that I added. But after we come to equilibrium, I only have products. Right? A weak acid is defined as an acid that only partially dissociates. So in this case, we would say that the equilibrium lies far to the left. And so, right, so this is again before dissociation. So we just added acid, so all I have is HA. But when I come to equilibrium for a weak acid, I have mostly the reactants remaining together and only a little bit of the products are being produced. And so if you noticed, for the strong acid, I use just a one-sided arrow because this reaction for strong acids we assume goes to completion. But I use the equilibrium arrows for the weak acids because an equilibrium is in fact established, right? We don't convert all the products into all the reactants into products. And in fact, most of the reactants remain. And so we would say that the equilibrium lies far to the left in this case. Right, just to give you an idea of what different Ka values might look like for weak acids. So these are a number of common weak acids, and you can see the equilibrium constants are all significantly less than 1. Now, the bigger the Ka, the stronger the acid is. So not all weak acids are equivalent, but for a weak acid, the value of Ka is always going to be less than 1. And in fact, for strong acids, we generally don't even report Kas. Right? We generally just assume these reactions go to completion. All of the reactants are converted to products, and so we don't worry about the equilibrium constant for those most of the time. All right, so I just wanted to finish up. I hate to ask you to memorize things, but in this case, you really have to memorize a few things. So there are 7 common strong acids, and you need to be able to recognize these on sight. So you need to have these 7 strong acids memorized. And in this course, if we encounter an acid and it's not one of these 7 strong acids, then we'll assume it's a weak acid unless we're told otherwise. And we'll talk about bases more in a couple days, but there are 8 strong bases. So I just wanted to go ahead and throw those on here as well as to show you a little trick on how to remember these. So if I put a line through all of the strong bases, and then I've got calcium, strontium, and barium hydroxide, right? That makes a little B. So that's one way that can kind of help remember what are the strong bases. All right, and this is what we'll start with in class. And so this will give you an idea of the types of things I want you to be able to do after watching this video, but we'll review all of these questions in class. Thank you guys very much.